Thank you so much to be here, and it's my big pleasure to introduce our colleague Ting Zhang from the George Mason University. She is an air pollution researcher, and her background was improvement between China and the United States. In today's seminar entitled Tracing PM2.5 Monitoring Health Burden and the Source Apportionment, she will introduce her approach through the model for shifting and monitoring PM5 and PM2.5, and then the impact of these pollutants to the human health.
Yeah.
Think parallelly.
Grazie. Buongiorno, everyone, and I'm very happy and feel honored to be here to give this seminar, and also feel very lucky to share my work with a wonderful group of the researchers here. And as you can see today, I'm going to introduce my work on PM2.5 from the monitoring to health burden assessment and then to the source apportionment. But before going to science, please let me make a brief introduction about myself. Okay, good now. My name is Ting. I was born in a small city called Danye in mid-China. That's a city surrounded by a lot of the mine industries. So when I was a kid, it was very common that people use the biomass burning for cooking. And also very common, we have a lot of the diesel-fueled trucks on the way. But believe it or not, whenever I got those smells of the biomass or diesel, I took a deep breath, love it. And then after that, I moved to Nanjing, East China, city near Shanghai for the university. My bachelor study was in geology, and my PhD study was in air pollution exposure assessment. I love field work a lot. And somehow, when carrying a personal, this is the personal monitor. Somehow, when carrying this personal monitor with a small black box with a light blinking, I got a lot of cautious look, even the looks from the policeman. And during my PhD study, I spent 2 years in Columbia University. Definitely, I have a lot of fun there. I was there learning more about the personal exposure measurement. After that, I have my first postdoc research in Nanjing University, working on the air pollution or more environmental risk related health burden, and then shift the focus to source apportionment and work on that in George Mason University. Most of the time, I work much harder than in the photo. Now, we're back to the science part, and so today, this is the outline of my talk today. I would first introduce the importance of PM2.5 and first exposure work during my PhD study, health burden from the first postdoc work, and the source apportionment from the second postdoc work, and then till now as a researcher. So why PM2.5 matters? And for decades, so the global health burden always shows that air pollution has been among the top 10 most risky environmental factors for the human beings of different ages. And among that, in 2023, about 8 million people, 8 million deaths was related to the air pollution exposure globally. And among that, 90% of the deaths is related to PM2.5. Historically, the disadvantaged communities also are more likely to breathe the unhealthy air, and this makes them more vulnerable. And for the environmental part, the air pollution, especially the particles, can lead to the vegetation damage and degraded visibility, and cause the damage for the materials. And for the climate, the PM can also influence the temperature, like the black carbon, the component can contribute to increase of the temperature, and the sulfate aerosol can contribute to decrease of the temperature. It's really so influential and can be so harmful. So given it's so harmful, then how much PM2.5 did we breathe? It's common for most epidemiology study, people use the PM level from the ambient, the outdoor level, or the monitors data from the central site to represent the people's exposure level. But according to a study in New York, we found the personal exposure levels can be more varied and can be much higher than the levels than the indoor, ambient, or the monitor sites. However, the 6-city study shows as the fine particle, that's the PM2.5, as the concentration increase, the ratio, the y-axis is the mortality rate. The higher the rate, the more risky it is. As the concentration of PM2.5 increase, the mortality rate also increased. In the most polluted city, the mortality rate can be 1.26 times as that of the cleanest city in this study. And similar to this Harvard study and many further studies, they also link the health endpoints to the PM2.5 mass concentrations. But the pollutions, they have so many different sources: power plants, cars, industries. And the recent HEI report shows that different sources can have different health risks. So recently there are more people thinking, instead of just focus on the mass concentration, we should also think about the PM component and the sources behind it, because they may matter more for the health concern. Based on this background, here are the research questions today I have. The first, how to assess personal exposure and what does it look like? What are the health effects, particularly on the vulnerable groups? And what are the contribution trends on main sources across time and space? Are the burdens distributed equally across population groups? The first part is about personal exposure. Personal exposure is jointly influenced by the ambient pollution level, the indoor sources, indoor ventilation system, and the personal activities such as like cooking, cleaning the room, or exposure to secondhand smoke or smoking, and so on. For me, while learning about personal exposure, I always use this sensor called micropen, placed in my pocket with the tube to my breathing area. Use this sensor for the monitoring. The sensor is perfect. It's very precise and very stable. But the only question is, when using it over time, there could be negative shifts in the real-time data. This is the raw data. We can, for some monitors, the shift can be up to almost 80% negative shifts. And use the traditional method, the shift can be somehow corrected, but still there are a lot of negatives. So I developed a round baseline and granulometric correction method. This method can fix most of the shift and enable more than 90% of real-time PM2.5 data for the further analysis. I also developed and applied some peak analysis method to the real-time monitoring data. We have the monitoring data for every 10 seconds. Generally, we use a minute average. So I apply this peak analysis method to the meaning the PM concentrations, and develop and also generate different peak indexes, including the accumulated peak area. And then I was curious, could the peak indexes better distinguish those have like some very strong indoor exposures and the strong indoor sources, and without the strong indoor exposures. So I applied the peak analysis method to the personal measurement, measurement for kids in New York. Some of kids, they have the secondhand smoke at home, and some don't have. And we can see this is the PM concentration for the kids from the two groups. We can, and for the accumulated peak area, this is the comparison between these two groups, and the peak index can better distinguish the kids with or without the secondhand smoke. And in fact, compared with other peak indexes, the accumulated peak area is the best one that can capture the kids' exposure. I also track the people's exposure in different micro environments on the clean days. the clean days is in China by then, so the criteria is by then it was 35 microgram per cubic meter, but now it has been much stricter. And then on the hazy days, that's like ambient at the outside the constraint is already above 200. So this is the x-axis ambient PM level, y-axis the pressure exposure, and the different points represent different microenvironment. We can see like on the clean days, generally the pressure exposures are higher than the ambient levels. This line is the y equal to x-axis line. The pressure exposure much higher, especially around some cooking sources. But then on hazy days, the pressure exposures were generally lower than the ambient and relatively less variable. Except for the microenvironments with the metro and this is the metro, the subway, and this is a lab. So these two places have very good ventilation of the AC system, so they have very good quality. But for the rest, they are kind of like higher exposure. And overall, the personal exposure level to the ambient, the pollution level, the ratio was 1.7 on the clean days and 0.85 on the hazy days. And we can see it's like, so this is like on the hazy days, ambient pollution level is the main drive, but on the clean days, the different microenvironments can be more influential, like the cooking places. Given that the clean days, using the ambient data can greatly underestimate the personal exposure. And for most cases, in most countries and areas, it's a much cleaner situation, and the personal exposure can be even higher than ambient levels. There is such an underestimation. And for this, then for my second work about health burden, I was also curious. When we see the burden from different views, could there also be like the estimated health burden could the estimated health burden be also very different? So this comes to the second part. So the answer is yes, underestimated. And for this part, I would like to focus on a serious study about the illness-related school absence for primary school students and the air pollution. Here, why I use the school absence data, because when a kid is sick, he or she may go to hospital or just go back home for their home nurse. If we only use the home, a lot of studies use the home visits as the health endpoint, but use that, there could be some underestimation. So with this hypothesis, we look more into the health burden. So I got over 700,000 illness-related primary school absence records from Jiangsu province in Eastern China during the academic year 2016 to 2017. The records were from over 2,500 elementary schools in the province. So in these records, there's like the date of the absence and whether the students go to have the diagnosed disease. Because every school have the health teacher or the health worker. The health worker would have a primary diagnose disease. And then later the kids will also report whether he or she goes to a hospital or just stay at home for rest. And with these records, we focus on two air pollutants, PM2.5 and ozone, and check their influence on the illness-related absence. Here, the x-axis is the percent change in illness-related absence when there's a 10 microgram per cubic meter increase in PM2.5 exposure or 10 ppb exposure increase in ozone. Generally, the higher the percent change is, then means the risky the exposure is. And then for this y-axis, it shows this is like I have different subgroups. The first is like all records means everyone, like ask for sick leave. Hospital visits is only for those who have gone to the hospital for further treatment, and home nursing, those stay at home. Here that more than 5 times, less than 5 times. This is like For some kids, they may just frequently ask for the sick leave, and some ask for less. So we have these different subgroups. And according to the study, we found that PM2.5 is related to the yearly related school absence for all the subgroups. And meanwhile, the ozone is mostly only related to those that frequently ask for leave. Or we'd say generally these kids, according to the further research, some of them have some basic disease. The air pollution makes the situation worse. And then now we know how the influence of the air pollution on the absence rate. Then how about if we see the air pollution influence in the view from the hospital visit records? So we make a comparison. We estimate the number of the influenced cases, and we estimate this number based on hospital visit record and based on the absence record separately. With this estimation, this is the yearly related absence cases related to the air pollution. And we found that if we use the hospital visit record, we can underestimate up to 42% of the yearly related cases related to PM2.5 exposure. When it comes to ozone, the number is slightly small, but still 18%, a high value. Now we know the health burden can be underestimated. Then how about the spatial distribution? So we further check the spatial distribution of the absence rate, and then we found the upper one, the more orange, the upper figure is the PM2.5 distribution. The more orange, the deeper the orange color means the higher the exposure. And for the one below is the daily absence rate. The purple one is the highest rate, and the yellow brown one is the middle rate, and green one is the lower rate. So we can see the areas with higher PM2.5 levels, they don't really have such high absence rate. And in some places, even the PM level is relatively lower, but the absence rate can be high. So why? And first, we try to check the socioeconomic and the geographic factors. And we found that in this check, in this modeling, it shows the more developed the counties with more developed economic status, denser road network and lower green space coverage will help increase the risk, while the counties with expanded expenditures in environmental protection and health will help decrease the risk. I think for this denser road and low green space, probably people can easily accept this because that means this is more polluted situation for on the personal level can mean that. But then why the more developed economic status? This is because this area they were more developed, they have a denser road network and also more anthropogenic emissions, more other exposures can lead to the increase of the risks. However, even with this estimation, we still found that they cannot totally explain the change in the spatial change in the PM2.5 related absence. Why? I ask myself. So we try to check some component, but we think about the component and then think probably it's the component and the source. And instead of learning about the source in the Jiangsu province, China, I moved to the US and do some source apportionment work in the US. Here, instead of our goal for this study is to figure out to get the daily graded source apportionment impact. And but why daily graded source specific impact? The PM2.5 can be related to the mortality even at a lower concentration of lower than 12 microgram per cubic meter, even lower. And then there are already studies shows that the source contributes unequally to exposure, health, and inequities. But how influential different sources are, the results are inconsistent among the studies. And also the current air quality standards, they were set for the ambient environment and mostly targeting the PM mass concentration. But if we want to further reduce the air pollution, like because now it's already low enough. In the US, it's below 8 micrograms per cubic meter now. How to further reduce that? We need more targeted, local level, regional level targeted regulations to reduce the source. And then the nationwide exposure fields, the daily fine scale ones, can help link the source to the health and the equality. So that's why we need it. And then how do we achieve it? This is a design work. First, we try to use the PM species observations from more than 300 sites across the US and use the positive matrix factorization, the PMF method, to get the site level PM2.5 source impacts. And then we use the EPA equates that's the emission inputs and the WRF inputs on meteorology, and use the chemical transport model to get the graded daily PM2.5 source impacts. And we use them as inputs and put them into the machine learning model together with some other source relevant data set to predict the daily fine scale PM2.5 source impacts, and then use those predictions to estimate the environmental justice accountability. The first part of this study is the PMF analysis. So first is like we have the study was the method, source apportionment method was applied to over 300 monitors. These monitors were from two networks, the chemical species network CSN and the interagency monitoring of protected visual environments, the IMPROVE. Why we use these two? Because they have a complete 1 in 3 day measurements from 2011 to 2020. That's our study period. And they also, these two networks, they examine the very similar PM species that can make us enable us to do apply the similar standards for the source apportionment. And also, we can see the blue dots that the CSN and the orange ones that they improved, they can have the spatial complementary. The CSN sites are mostly like in the eastern US, more urban. And the improved sites are mostly in the western US. They were mostly in the national parks, national wilderness, and things like more rural areas. So they have this spatial complementary thing can help us display the source contribution in different areas and the different geographic areas. We developed a streamlined dispersion normalized PMF method and applied it to each monitor stations. This is we try to streamline each steps, but among all of them, today I want to highlight this part is the PM source apportionment. So PMF method is like it's using the covariant species to derive factor that can be assigned to one source. Just for example, this is a source profile detected from the PMF method. This is different species we use, and this the concentration is how much concentration a given species contributed to each factor. And this is on this y-axis on the right side explains how many percent of this species contribute to this factor. So, like for example, like for the sulfate, we can see it's around 75%. This for this side, around 75% of the sulfate ion and around 40% of the ammonium ion contributed to this factor. Because of these two features, the covariant species, so we detected as the sulfate source. And similarly, for the source like secondary nitrate, dust, and sea salt, they have relatively stable and fixed covariant species combinations. So we wrote a program to automatically assign the corresponding factors to these sources. And then for some other sources, the non-tailpipe biomass burning, traffic, and another important one is like the industry, not on this side. Industry for them, because the covariant species for these sources can be different in different counties, in different cities, and different from year to year due to some regulation changes. So for these ones, we will collect the local emission information, the geographic information, and use the manual, do the manual check and manually appoint these sources. Now, after this, we have the source apportionment data, the daily 1 in 3 day source contribution data from all this, from so many sites. Then how about the trends on national level? From this one, we can see this the 8 main sources we detected on the x-axis, and the y-axis shows we use the Pearson method to check the chemical trend, and this concentration is like 1 point represent one side. So it's like the whether like the concentration overall they are overall decrease or increase, and this is a fraction contribution, decrease or increase. The orange one represent increase, the green one represent decrease. So we found that the sulfate is the decrease in both concentration contribution and the fraction contribution. In fact, the sulfate is a main driver in them, because we can see there's almost like from almost all the sites, there's the sulfate concentration decrease. From 2011 to 2020, the US PM level dropped by like around 2 microgram per cubic meter. And according to our studies, 91% of this drop is from the secondary, is from the sulfate. And then for nitrate, the concentration and the fraction also slightly decreased, but not so notable as the sulfate, and similar for the salt. Meanwhile, the biomass burning and SOA source, that it shows the increase in the concentration and the fraction, and especially like for the traffic and the industry, they have slightly decreased in the concentration, in fact, because of all the regulations, but because the overall PM, the total PM level is decreasing. So the fraction contribution of traffic in the industry, in fact, increased. And two other sources, they don't have very notable trend. And because of the very big increase, like the decrease in the sulfate, we are curious. It's the main drive behind the PM decrease in the past decades. We are curious more details. So we have separated the US on one side, grouped them into 9 regions and check the regional trend. And the white points represent each mountain site, and the darker the color, the higher sulfate PM2.5 in this region. And then here is at the field, and for these trend lines, they represent the sulfate PM2.5 trends over the study period. And we found the highest, the sulfate PM2.5 generated higher in the East US, and meanwhile, the highest decrease is also from the Eastern US, like Mid-Atlantic, Southeast, Eastern, North Central. This is kind of, in fact, very interesting. It's matched very well with the coal power plant related PM2.5 from another study. High concentration in the East in the back to 2013, and then also the highest drop of the coal power plant related 2.5 was also in the East areas. So why they match so well is because of the component. The coal power plant is the most important sources for sulfate PM2.5 in the US. And in comparison, the biomass burning SOA gradually dominate the PM2.5 pollution. By the 2019, already there are like 48% of the sites, their dominant sources is the biomass burning. Here I group the biomass burning and SOA together because based on the species we have, we cannot totally separate them too. And so this, we can see something interesting. This figure, this study shows like the smoke-related PM2.5 in the US, the same period as our study period as ours. and the smoke PM2.5 was highest in the northwest of the US. Ours kind of still higher in the southeast and the east area. And our special pattern is more similar to the SOA, the secondary organic aerosols. This is because on the east side, it's like there were most of them, they were the urban sites. So there are a lot of urban sources like the home cooking and the volatile chemical products, something like that. They contribute to the SOA. And especially for this part, there's the prohibited burning. So they also contribute to this source. And then another part, when we have like all these site level source contributions. Now next it's like we use the chemical transport model to get the graded source impacts. This work is mostly conducted by a PhD student in our group. So the CMAC, it was run on a resolution of 12 square kilogram. Especially we use CMAC ISAM, the integrated source apportionment method, because it's a tagging approach for quantifying each source PM2.5. And we use the CMAC ISAM to estimate the graded source impacts from power plants, fire industry, and so on. And then now we come to the machine learning part. We use the output from the PM2.5 as a dependent factor for our model, because the assumptions here is the PM2.5 source impact was estimated based on the filter-based measurement. So it's kind of like a ground truth. And then we use some other predictors, some of the shared predictor, like the meteorology, land type, something day, week, month, year, and the CMAC ISAM source impacts. For each source, we have different CMAC ISAM source sector. For example, for the traffic, we have the diesel transport and the gasoline transport and some other detected transport. And also related ambient gas pollutants. And also for each source, we have some specific predictors from other data sets. For example, for like the biomass burning, we use the HMS smoke product from the NOAA for the prediction of the biomass burning. And we use the commuter method and the time road proximity and road length, some data set like this for the prediction of the traffic exhaust. We have used different models, and today I'm going most focus on the results from the random forest model. So every time we for the model training, every time we randomly select 80% of the monitors to train the model and then predict the rest of 20%, and we repeat it for 50 times and use the averages from all the 50 holdouts to represent the final daily source-specific impacts at each grid point. We in the training and in the model training training process, we make sure each monitor appear at least one time in the training set and at least one time in the testing data set. And then we evaluate the performance of the model for each holdout iteration. So in fact, the performance was kind of good. Here we use four indexes: the mean bias, normalized mean bias, the Pearson correlation value R, and the root mean square error. And the mean bias is kind of small, the plus or minus 0.05 microgram per cubic meter, and the R's generally higher than 0.85. It's a good modeling performance for this one. And especially for each source, we found the best performance is for the sulfate. It has very, very low, especially contribute relative to its concentration, low root RMSE value and very high R. This is probably because the sulfate trend is so consistent in both PMF and the CMAC inputs. So they can very well produce this consistency in the modeling. And then for the biomass, it has very high RMSE value, but the bias was kind of low. This suggests there are some extreme biomass contributions. We might have missed that. This is something we try to fix for now. And then unfortunately, the prediction for the secondary nitrate is relatively poor compared with other sources. The main reason is like the seminari model, it cannot very well catch the nitrate iron concentrations over time. So for the rest analysis, we focus more on the other four sources, the traffic, surface, the biomass burning, and the dust. We get the daily fine-scale PM impact from all the 5 major sources. Now this the spatial resolution for this one is not super fine, it's like still 11 multiple 11 square kilometer, but we are working on the 1 multiple 1 kilometer predictions for now. And for this one, we can see the spatial changes, like for each source for a certain day, there's a spatial change very notable. And on different days, this is like we use like 4 days from 2019. Each day represent different season to show the daily results. For certain sources, the spatial contribution for the sources also different from day to day. And also definitely for different sources, the contribution difference is more notable. And also with this daily data, we can see the plumes from the individual emissions. Just like for the biomass one, we can see the single plumes on October 15th, 2019 in the Midwest of the US. And with this daily predictions, we got the annual trend of the different sources. This is the trend, annual contribution, annual impacts in 2019, again, 2019. And the orange one there, the uncertainties. Uncertainties like we estimate the standard deviation for every day and every grid point from the 50 holdout iterations and get a standard deviation and use that standard deviation divided by the concentration, then we get the uncertainty. Except for the secondary nitrate, the standard deviation was high for the biomass and then followed by surface, dust, and then the traffic. And and then for the uncertainties, it is the highest for the traffic. Especially, we can see the green-purple colors represent the rural sites. The uncertainty was especially high in the rural areas. This is probably because in the rural areas, the traffic concentration contribution is lower, so the relative uncertainty just increased. And with these predictions, we further estimate the environmental justice. We can see to check the source air pollution exposure and equity, we match the exposure data with the census tract. Census tract is a unit with the population of 2,500 to 8,000. 2,500 and 8,000 is kind of like a relatively small geological unit. And we identify the exposure difference among the groups classified by different categories, such like the races, the genders, and house incomes. We do this to identify the groups with unevenly high source-specific exposure and to identify while the source inequity improve, worsen, or persist by source and by region. And here I'm going to show mostly the results from the race. And first we can see, shows like the demographic distribution across census tracts for different races. For the white group, definitely there is no big change. And then for the American Indian, Hispanic, and for the Black group, we can see there's very notable the geographic clustering. For example, the Blacks was they were mostly like in the Southeast US, and the Hispanic was mostly like in the West and Southwest of the US, like some were like Kansas with deserts also. This will influence their exposure, we can see later. And for the Asian group, it's a bit specific. It's not demographic clustering according like which direction. It was more different, the distribution was more different, whether it's rural or urban sites. So for the Asians, they were mostly in the urban areas of the US. And then we found a varied weighted exposure for the different population groups. For this figure, it's like the x-axis is the different in year, y-axis is the absolute population weighted concentration difference between a certain group, certain race group, vs the exposure of the total population. So this is the absolute difference for them. And from this we can see for the black people, generally they were 10% higher exposure for the nitrate, secondary nitrate traffic and biomass. Something very interesting, they also have consistently high surface exposure from the beginning to starting to until 2016, 2015, 2016. And something very happy to see is this absolute difference gradually dropped to almost zero by 2020. That means the inequity in surface exposure for the black disappeared. It's a good thing because it means the regulations for the air quality control, it helps a lot. And then for the Asian group, they have higher exposure for the traffic, biomass, and nitrate. And Hispanic, they have similar high traffic and nitrate exposure. And also because, just as I mentioned, they were near the Kansas, the southwest of the US, so they have very high dust exposure. And for the American Indian, they have relatively high dust exposure. Something else interesting is like when we look into each source, the group with the highest exposure for this source is always the same. Like for Asians, always suffer the most from the traffic among all the races, and black always suffer most from the surface, and the Hispanic always suffer most from the dust. So this is the exposure burden, it shifts, but who suffer the most from the certain sources remain the same. And this study is still ongoing. We're doing more of the regional difference change, regional pattern analysis, and so. And the key findings till now for this part is the changes in most important the regional sources is like the dominant source shift from the surface to biomass burning and then SOA, and increase the PM2.5 from some of local sources, mostly the increased fraction contribution. And the environmental justice analysis tied to the sources, most exposed group did not change, even exposure to many sources changed. And we can use this fine scale source impacts for the use in the future for epidemiology study, other risk analysis, and environmental justice analysis. So this is my work from the PhD personal exposure, curious about the exposure level. And then I was thinking, since with this exposure, what health would be like, then the health burden. And then I figured out a lot of influential factors that are not enough to explain the special difference in the health burden. I went back to the exposure, but this time it's a different exposure, the source-specific exposure, and then use that for the environmental justice analysis. And all these studies was finally to inform evidence-based air pollution policy, so that we can have a cleaner air, reduced burden, and a sustainable future. And that's my study for all. And yeah, we've been breathing during this whole talk. What do we put into our lung? Thank you.